So here we are, week 9. We're more than halfway through. Woohoo! And you're the survivors. How's that feel? Crickets. Okay, fine. So here we are, week 9.
Like we're all surviving, holding on to survive.
But what I'm learning from yoga is hold on, but don't hold your breath. Keep breathing.
Yes.
Yes. Sometimes I hold my breath. Let me let this person in. Oh, good. It's Eli. I love them. Okay, so I haven't changed our start here button, and I will. But anyway, this is week 9. This is where we are. And you can always go to modules, and then you can see all the modules we've done. And then you can't see where we're headed because I haven't published that yet. But here we are. Solubility of ionic compounds. This is a worksheet that you're going to turn in. And then the video is a video that I made yesterday. I think it was yesterday. It all blurs. And at the video, we worked through a few problems, and then some students stayed and finished it and asked questions. But here's the video of the Zoom yesterday that talks about how to solve this worksheet. Okay, and then the next page is our meaty content page. So using balanced chemical equations was something that I assigned last week, but it wasn't on our exam. And so some of you maybe did everything else to get ready for the exam and then took the exam up to yesterday midnight. And so you haven't watched these videos yet, which is totally fine. Just watch them now. And then there's a FET that I recommended that you go play with. And now I have an assignment for that. So go do that FET. Download when you click this link, you're going to get the worksheet. You can download the worksheet. You'll go to the FET. You'll get the idea of how this works, fill out the worksheet and upload it all at the same one link. And then once you have read the text, watched the videos and done the FET activity, here are some worksheets to do for practice and points. And so tomorrow I'm going to work through the sulfur addition. Friday, I'm going to work through phosphorus, and Saturday I'll work through nitrogen. If you are able to download these and attempt these and maybe do these first, you might decide you don't need to come to Zoom, or you might come to Zoom just to hear me do them, to hear me walk through the thinking. But for these 3 worksheets, the answers are there. And then you're going to combine your files and upload it. And I think I need to put a link here. I haven't done that yet, but I will. So today, I'm going to talk about stoichiometry. There's no worksheet for today, but, actually the solubility was Monday. I see that now, but hopefully you'll take notes and ask questions. So here we go. So we're at the place in the class where we're actually doing chemistry, and chemistry involves chemical reactions. And how do we represent chemical reactions? We write chemical equations. And when we add the coefficients, we have balanced chemical equations that allow us to make predictions. And so that idea of using a balanced chemical equation to make predictions is called stoichiometry, which is a big word. But it really is just this. Once you have an equation where you have correctly written the formulas, and now you want to mass balance it, which means you want the same number of each kind of atom on the left of the arrow as the right of the arrow. To do that, you add coefficients. That's what I talked about yesterday in Zoom. I haven't put that one up yet, but I will put it up soon. And then stoichiometry is just saying, well, if I have a starting amount for nitrogen monoxide, I'm told I have 10 grams. Can I figure out how many grams of ammonia I can make? And that process is called stoichiometry. And the math looks like this, or the roadmap. We're going to go from grams of one thing, in this case it's a reactant, to moles. And to do that, we're going to use the molar mass that we find on the periodic table. And then we go from moles of one thing to moles of another. In this case, I'm going from moles of one reactant to moles of one product. And that step, using that ratio, is called stoichiometry. using the fact that 2 of the reactant molecules are consumed every time 2 of the product molecules are formed. That's stoichiometry. So for that one, I'm going to write balanced equation. And then we can go from our moles of ammonia to our grams of ammonia using the molar mass given on the periodic table. So grams to moles to grams is the roadmap. The trick is, and those are skills you already have. Using the balanced equation, this one we're going to add, it's a very easy step. The trick is to read the problem and interpret it correctly. And so that's what I want to walk you through today and then the next 3 days for Zoom. So I'm going to start with just one reactant. We know that we have 10 grams of this reactant. I want to know how many grams per mole, the molar mass. So I look at the periodic table and I see that nitrogen is 14.01 grams per mole. Oxygen is 16 grams per mole. So I have 30.01 grams per mole as the molar mass. I'm going to use complete units, which means I'm going to say grams nitrogen monoxide per mole nitrogen monoxide. Why am I doing that? Because in a minute, I'm going to say for every 2 moles of nitrogen monoxide, 2 moles of ammonia are produced. So the stoichiometry step is where I'm crossing over from one kind of moles of one kind of thing, to moles of a different kind of thing. And then I need to figure out the molar mass for ammonia. Oh, there's 3 of those. So let me make sure that I have set this up correctly on my train tracks. Grams of nitrogen monoxide, cancel. Moles of nitrogen monoxide, cancel. Moles of ammonia, cancel, and I'm left with grams of ammonia. And the question was, how many grams of ammonia? So I will plug that into my calculator. You know that sig figs are important, so let's see what we have. I'm starting with 3 sig figs. Grams are masses. Masses are things we measure. We count the number of digits. A molar mass has a limited number of digits. I'm just using the one that we have on our periodic table that goes to 2 past the decimal, so that's 4 sig figs. This step, which is the stoichiometry step, going from moles of one thing to moles of a different thing, has unlimited sig figs. And then our molar mass for ammonia has 4, so my answer should have 3. 3 is the fewest number. And there's my answer. That is stoichiometry. Now, there are places where it can get a little more complicated. We'll do that. And there are places where students make mistakes. So I want to highlight this idea. For the stoichiometry step, where I went from moles of one thing to moles of another, that step that has unlimited sig figs, I have to use the coefficients in front of the formulas. If I was to reduce that and say 1 mole of ammonia for 1 mole of nitrogen monoxide, it would be wrong. I have to have a 2 here because of this 2 here. I have to have a 2 there because of that 2 there. So I have to use the coefficients in the balanced equation for the stoichiometry step. The next place that sometimes students make a mistake is that when they're doing the molar mass steps, they start using coefficients, but that doesn't make any sense. A molar mass is how many grams is 1 mole. So for the molar mass steps, don't include the 2 because there's no 2 moles in a molar mass. So if you were to double this and write 60.02 grams per 2 moles, it would be wrong. Okay, so that's stoichiometry, but we can do more with that. So first I want to make a roadmap here. And the roadmap is just, I want to put some big ideas in your head. And this is a baby roadmap that's going to grow larger. And in a second, I'll show you by the end of the semester how large it can be. But I'm starting with the idea that I can get to moles of something with grams. If I know the grams of A, I can get to the moles of A, and I use the molar mass to do that. I can go from moles of A to moles of B and back. So this is like me saying moles of the reactant nitrogen monoxide to moles of the product ammonia, and that always requires a balanced chemical equation. Once I get to moles of B, I could go to grams, again using a molar mass. So that's what we just did. Are there other ways that we could get to moles of A? Sure. Let's say that you had the number of molecules. You could use Avogadro's number to get to moles of A. Avogadro's number is the same for each because all that matters is how many pieces in the group that we call a mole. Pretty soon we're going to get to things happening in solution. And so we're going to start with some volume of A. And in that case, we're going to be able to use a concentration unit, maybe molarity, to get to moles. So this is next week. But just the thing I want to show you is there's several ways to get from kinds of A to moles of A. But the only way to get from A to B is through the stoichiometry step, using the balanced chemical equation. Now, sometimes when we have two reactants, we have more of one than the other. We have more than we need to produce the product. It's kind of like if you're making a cake and you have 3 eggs and a lot of flour, and the cake requires 3 eggs, you can only make 1 cake. You might have flour left over. Very rarely do we have the right amounts of starting material to produce something. Usually one amount of starting material could produce more product, but we're limited by the other starting materials. So that's what I want to do here. This time I'm going to do stoichiometry, but with 2 starting amounts. And as soon as we have 2 starting amounts, we call this limiting reactant. Stoichiometry. What that means is one of the reactants is going to run out and limit how much product we can make. And so we need to figure out which one that is. A way to do this that always works is to just go grams to moles to moles to grams of the product. So I might start with my grams of nitrogen monoxide and go to moles of nitrogen monoxide. Use the 2-to-2 ratio to get to moles of ammonia, and then the molar mass to get to grams of ammonia. I do that with one, and then I do that with the other. Grams to moles of the other, to grams. And then I compare the 2 answers. And whichever is smaller is the right answer. And whichever produced the smaller amount is the limiting reactant. So that's what I'm going to do, just that whole grams to moles to grams step, like I did here, but I'm going to do it twice.
Will the product always come first, and then
No,
kind of the byproduct is the second, like water is kind of the byproduct?
right. No, it just depends on what the question's asking. The reason I didn't pick water is because a lot of what we do is going to have a lot of extra water, but I could have picked water. So it's just
And
the
you
question.
go through the same process?
Same process, yeah.
Okay, thank you.
Sure. Thank you. Okay, so we've done grams to moles to grams, and we came up with some answers. They have different sig figs because the starting amounts have different sig figs. Both things were measured on a decigram balance. I went to the 10th of a gram, but I had more nitrogen monoxide, more mass of it, and that's why it has 3 sig figs. Okay, so now I've done my grams to moles to grams, and I've come up with how many grams of ammonia nitrogen monoxide could produce, and how many grams of ammonia hydrogen could have produced. And we see that nitrogen monoxide produced less. It ran out before it could get to 20 grams. When did it run out? It ran out at 7.677 grams. Or maybe 6.6, depending on how you round. And so we cross out the other answer. We don't do anything with it. Why couldn't we make 20 grams? 21 grams? Because we didn't have enough nitrogen monoxide. It ran out. Nitrogen monoxide is the limiting reactant, and hydrogen was in excess. So a common question might be, well, how much hydrogen was left over? And so we're going to do that one next. To answer the question, how much excess reactant remains, RXT means reactant, and in this case, it's hydrogen. We're just going to take the starting amount for hydrogen. 6.2 grams were available, and we're going to subtract how much was needed. We need to find that number. And the difference is how much is left over. To find the amount that we're going to subtract, we're going to start with our limiting reactant and go grams to moles to hydrogen. So now we're headed to grams of hydrogen, and then we can find out the number that we're going to subtract. So I'm going to start with my limiting reactant, 13.5 grams of nitrogen monoxide. And I'm going to go from grams of one reactant to moles and use the balanced equation to go to moles of the other reactant, and then to grams. And then those grams I will subtract from the available grams to see how much is left over. Okay, so there are a lot of you here, and I can see maybe 3 screens of 3 videos are on. You can always write a question in chat. I'm going to go on, but if you have a question, please ask or please type. Okay. So limiting reactant stoichiometry is just, we're going to use a balanced equation to answer some questions. And the questions might be, how much product is produced, or how much of the other reactant is needed? If we're given two starting amounts, that's when it becomes limiting reactant. Limiting because one of them is going to run out. Okay, so there's a lot of ways to get to moles, but to do limiting reactant stoichiometry, we have to take the moles of each reactant and then head to whatever product has been asked in the question and find the moles of that. We could go, once we find the moles of that, we can stop there, compare, we see which is the smaller number, and then go from the smaller number to grams to answer the question. Or we can just go grams to moles to moles to grams and look for the smaller number. And the larger number we just cross out. What we found when we do that is called a theoretical yield. So yield just means how much was produced, and theoretical means, in theory, given these starting amounts, we could have made this much. But in reality, do we usually get 100% reward for our effort? No. Usually we get less than 100%. So there's a thing called percent yield. So theoretical yield is us using stoichiometry and the balanced chemical equation, and we're doing calculations. So it is the calculated value. The actual yield is what is measured on a balance. It's the actual amount that was produced. So let's say that we did all this. I'm going to go ahead and give you some new starting amounts. Let's have 10 grams of nitrogen monoxide and 2 grams of hydrogen. And I want you to find how many grams of ammonia. And then we're going to say, well, that was theoretical. How much was actually produced? Let's find the percent yield. So go ahead and you do all the steps with these new numbers. So I've gone through my steps and I've come up with 2 amounts produced by theory, but only one is right. So 5.68 grams is a smaller number than 17 grams. Compare and pick the smaller number. 5.678 grams, that happened if nitrogen, oops, I said dioxide, I don't mean that. If nitrogen, that happened if nitrogen monoxide is a limiting reactant. And so we now know nitrogen monoxide was a limiting reactant. One question might be how many grams of hydrogen remain? That was a problem we did previously. But this one is about percent yield. So in order to complete a percent yield question, we have to be told the actual yield. If we were in the lab, we would measure it. But since we're not in the lab, the actual yield has to be given in the problem. And now we're going to take our actual yield, divide by our theoretical yield, multiply by 100%. And when we do that, we will have a percent yield. Our percent yield is going to have sig figs that are limited by 2 numbers. We have to compare the sig figs in the actual and the sig figs in the theoretical and pick the smaller number. So my actual is 4.7 grams. My theoretical in this case was like 5.78 grams, or 5.68 grams. Two sig figs, 3 sig figs. My answer can only have 2. 83% yield, which is actually very good. When you take organic chemistry and you look for your percent yield, if you get 20% yield, call it a win. because in real life, it's very hard to get 100% return. So probably if you don't have questions, it's because you haven't done the work yet, which is totally normal. This is how life goes. So limiting reactant stoichiometry sulfur edition. I have put a link here for tomorrow, and you can find the worksheet that walks you through some questions. And then at the end, there are some answers. Oh, interesting. This one doesn't have answers, but the other two do. And it really doesn't matter which one you pick first. They're all the same idea. So here's some questions, and then there's your answers. And the answers are correct in their sig figs. Now, actually, these might depend on the periodic table you use. I'm not sure. Now, you can find those three things here or under this week's module. So we're in week 9. In week 9, we're talking about limiting reactant stoichiometry. Here are some videos that you should have watched last week. It's okay if you didn't, if you were spending your time doing other things like, getting ready for an exam, but watch them now. Here's a FET that has a puzzle, like a game, but there's also an activity, something you need to turn in. And then here are the same 3 worksheets. So there's 1 page, 2 page, 2 page. There's 5 pages all together. It's going to count for 50 points. You're going to combine your files and upload them, and I'll give you credit for doing them. The credit is for the work, not for the answers, obviously, because you have the answers. Why do I give you the answers? Because it's nice to know if you've done it right. So before you come tomorrow to Zoom or before you watch the video, it might be a good idea to try the sulfur edition and then check your answers and see if you have specific questions. And I can answer those specific questions at the beginning of Zoom. So here's 3 worksheets that you need to do. Those are the 3 Zooms coming Thursday, Friday, Saturday, and they are worth points. So you can do them with me or you can do them on your own. It always is a good idea to try doing them by yourself without your book. And then if you run into stumbles, use your book. And then if you are still struggling, maybe watch one of these videos, but hopefully you've already watched them, and then get questions answered. That is a normal process for learning. Learning doesn't happen because we watch somebody perform in front of us. Learning happens when we do it alone and we see how far we can get. And that's when we find out what our questions are. So that's how I suggest you do this. But of course, you're free agents. You'll do whatever you prefer. That's totally fine. But so that's my plan for this week. The more practice, the more comfortable it becomes. When we do this on the exam, I'm going to have to use the periodic table just because there's Google up there. But if you do it on your own, you'll become comfortable with it. And then that won't even be a problem when we get to exam 3. Questions? Nope. Okay. In that case, we're done. You're free to go. And if you want to stay and ask questions in person or chat, that's totally fine.